For 130 years, the kilogram was a literal lump of platinum iridium locked in a vault near Paris. If a few atoms rubbed off, the entire world's definition of mass shifted with it. So how did we replace a physical object with something that can never tarnish, drift, or be lost? The answer rewires how we define reality itself. The physicist Ernst Mach observed that time itself isn't absolute. It's an abstraction we read of the change in things. Measurement is always tied to something that moves, decays, or vibrates. To understand the revolution that freed us from that platinum lump, we first need to see what the modern system of units is built from. Science needs one shared language of measurement. That language is the Système International, abbreviated SI. It rests on 7 base quantities, each with its own unit defined independently. A base quantity can't be built from the others. Everything else in physics is a derived quantity, assembled from these 7. Get the foundation right and every other unit follows automatically. Here are all 7. Time measured in seconds, symbol S, length in meters, m, mass in kilograms, kg, electric current in amperes, A, temperature in Kelvin, K, amount of substance in moles, mole, and luminous intensity in candela, CD. 7 quantities, 7 units. From these, the speed of a sprinter, the output of a power plant, every measurable thing in nature can be expressed. Mechanics, the physics of motion and force, needs only 3 of these: the second, the meter, and the kilogram. Together they form the MKS system. There's an older alternative still used in some fields, the CGS system, built on the centimeter, gram, and second. Same idea, smaller scale. With these 3 units in hand, watch how every other quantity in mechanics simply falls out. Start with velocity, the change in position divided by the change in time. Meters divided by seconds gives meters per second, which we write as m times s to the minus 1. Now move on to acceleration, the change in velocity divided by time once again. Take meters per second and divide it by seconds one more time. That gives meters per second squared, written m times s to the minus 2. Each step simply stacks another second into the denominator. Now let's build the unit for force. Force equals mass times acceleration. Mass is measured in kilograms, and from before, acceleration is measured in meters per second squared. So multiply kilograms by meters per second squared, and you get kilogram meter per second squared. We give this combination a name, the Newton, with a symbol capital N. But the Newton isn't some brand new fundamental thing. It is literally kilograms times meters times seconds to the minus 23 base units wearing a single name. To make it concrete, a 1 kilogram object accelerating at 1 meter per second squared feels exactly 1 Newton of force. Keep going. Energy equals force times distance, so we multiply the Newton by another meter. Kilogram meter per second squared times meters gives kilogram meter squared per second squared. We call that the joule, symbol capital J. Push that 1 kilogram object 1 meter and you've done 1 joule of work. Finally, power equals energy divided by time. Divide the joule by 1 more second and you get kilogram meter squared per second cubed, the watt, symbol capital W. Do that 1 joule of work in 1 second and you deliver 1 watt. Velocity, acceleration, Newton, joule, watt. Each one is the previous unit combined with a single base unit. Derived units aren't arbitrary inventions. They're transparent algebra, built from the second, meter, and kilogram. But this raises a deeper question. What defines the base units themselves? For the kilogram, the old answer was that platinum cylinder. The problem, a physical prototype carries experimental uncertainty. It can be scratched, gather dust, or lose atoms. Measure it twice and you might get slightly different numbers. Tie the world's mass standard to one object, and the standard is only as stable as the object. On May 20th, 2019, the system changed. All 7 base units are now defined by fixing the exact numerical values of 7 constants of nature. Reverse the usual logic. We no longer measure the speed of light. We declare it to be exactly 299,792,458 meters per second, and treat that value as invariant, the same everywhere, forever. Once the speed of light is fixed and the second is fixed, the meter is automatically defined. The distance light travels in that fraction of a second. Fix the number, and the unit defines itself. The kilogram followed the same path. Instead of a metal cylinder, mass is now anchored to the Planck constant, fixed at 6.6260715 times 10 to the minus 34 in units of kilogram meter squared per second. One crucial point, the sizes didn't change. A meter is still a meter, a kilogram still a kilogram. Only the definition changed, and with it, the precision and permanence. Humanity anchored its measurements to the fabric of the universe, constants identical for everyone, everywhere, always. No vault required. The universe holds the standard now.